Yes, there.
Good?
Yeah.
Okay. Sorry about all that.
That's okay. Thank you.
Okay, so welcome, Nikki, again.
Okay, thank you. All right, thank you so much. So I'm going to be talking about structural identifiability of biological models. Okay, so the motivation for my talk today is this idea of an unidentifiable model, which I'll explain more precisely in a couple slides. But to motivate this, let's say we have these two models. I'll call them Model 1 and Model 2. These are both linear systems of ODEs. And notice these models are quite similar. They both have a state variable of this form, x1, x2, x3. They both have what's called an input of this form, u1, 0, 0. They both have what's called an output of the form y equals x1. Notice the only difference between these two models is the 0 pattern in the matrices. So for example, in the first model, the 2, 1 entry is 0, whereas in the second model, the 3, 2 entry is 0. So these two models are quite similar, but what's interesting is that this first model does not have what's called an identifiable scaling reparametrization, whereas the second model does. And I claim that one reparametrization is this one I've listed here. So in the talk today, I'm going to discuss what it means to have an identifiable scaling reparametrization. I'll talk about which models have them and which models don't, and I'll give an algorithm to find an identifiable scaling reparametrization. So by the end of the talk today, you'll see how we came up with this reparametrization here.
So these models are just, are they artificially created or they?
These were sort of artificially created, yes. Mm-hmm. Okay. So I'm going to be talking first about identifiable reparametrizations of what are called linear compartment models, and we'll talk about scaling reparametrizations, and we'll give some necessary and sufficient conditions. And then later in the talk, I'm going to be sort of talking about this problem a bit more in a bit more generality, and talking about this idea of finding identifiable functions in general. And I'll talk about sort of some heuristic approaches to doing this, so using Gröbner bases and also using some linear algebra techniques. Okay, so that's the plan. Okay, so let's talk about structural identifiability. So we're going to be looking at ODE models. They're often called state space models, and they have the following form. They look like x dot equals some function of possibly t, x, u, and p. And then we have some other additional equations, y, some function of x and p, where here these functions f and g are rational functions of their arguments. So what are each of these terms? We call x the state variable, we call u the input, and we call y the output, and p is the parameter vector. So in these problems, the parameter vector is unknown. So the identifiability question is about finding which unknown parameters of our model can be quantified or determined from input-output data. So if all of your parameters can be determined from input-output data, that's great, and we say our model is identifiable. However, if some of your parameters can take on an infinite number of values but yield the same exact input-output data, then that's clearly bad, and we say that's unidentifiable. And that's the case I'm going to be focusing on today. Okay. So the motivation for talking about identifiability comes from biological models. So here's a very, very simple biomodel. So let's say in a lab, they're testing the effects of a drug on the human body. And let's say the drug is administered in the blood. So that represents the input to our system. And then let's say the drug is exchanged between the blood and an organ, for example, the heart. So that's represented by these arrows here. And then let's say the drug leaves the system. So it leaves the blood, it leaves the organ. And then let's say we want to measure the drug concentration in the blood. That represents the output to our system. So we can translate this picture to a mathematical model. This is called the linear two-compartment model. We have our input U1, that's our drug input to the system. We have these two state variables, x1 and x2. Here, x1 represents the drug concentration in the blood, and x2 represents the drug concentration in the organ. Then we have these two exchange rates, A12 and A21. These are unknown parameters. These are constant rate parameters, and they represent the rates of transfer from one compartment to another compartment. And then we have these leak rates, again, unknown parameters, A01 and A02. Again, these represent rates of transfer from those compartments to outside the system. And finally, we have our output Y, our measured drug concentration in the blood. Okay, so we can form the very simple linear first-order ODE system of equations that corresponds to this picture. So for example, notice in the first equation, the coefficient of x1 has the negative sum of all the outgoing arrows. The coefficient of x2 has the incoming arrow, and then we're adding u1 because we are inputting into compartment 1. Similarly for the second equation, and then y equals x1 means we are measuring from compartment 1. Okay, so the important point about this system is that the only known quantities are the input u1 and the output y. So the 4 parameters and the unmeasured state variable are all unknown quantities. Okay, so then...
Can I ask a question?
Yes,
In the actual modeling of medications,
yes.
Is this the thing that will be used actually?
Yes. So this is in typical pharmacokinetic applications. This would be your system of equation.
And not something more complicated, but actually something like this.
Sure, exactly. They actually do very simple models like this. Mm-hmm. Exactly. Yeah. So these are common in pharmacokinetic applications. Very, very common. Okay. So our question for this very, very simple model, this is a super simple model, the question is, can we determine these 4 parameters from our input-output data? Okay, so let me talk a little bit more in depth about what types of models I'm going to be discussing today. So these are called linear compartment models. So let me define them now. Let's say G is a directed graph with vertex set V and edge set E. And let's say we have M edges and N vertices. Then we're going to be looking at models of this form here, where we're going to say X is our state variable, U is our input, Y is our output. And I'm going to be making a couple assumptions today. So the first assumption I'm going to make is that we're only going to be looking at models that have a single input and a single output in the first compartment. So what that does to our system is this vector U is just going to be of the form U1 and then a bunch of zeros beneath it. And then Y is going to equal X1 because we are just measuring from compartment 1. Okay, so that's our first assumption. So what does the matrix A look like? So A is basically just a weighted adjacency matrix. So for the off-diagonal elements, they're equal to Aij if there exists an edge from the jth vertex to the ith vertex. Otherwise, they're 0. And for the diagonal elements, what do those look like? So the diagonal elements have the negative sum of all the outgoing arrows. So the negative sum of any leak terms, so those are our leak terms, and then negative sum of any outgoing edges. All right, so that brings me to my next assumption, which is I'm only going to be looking at models today that have leaks from every single compartment. So what this means is that we're assuming then that this leak term is non-zero. So because I'm assuming this leak term is non-zero along my diagonal elements, that means that all the entries in my matrix are independent. So let's just rename them to make our lives simpler. Let's just rename the diagonal elements AII. Okay, so we have this nice simple form for our weighted adjacency matrix. Yes?
Is this actually a frequently used assumption in...
Oh, yes.
The leak situation often occurs that everything leaks.
I mean, it depends, yes. Yeah,
depends on medication maybe, but
sure.
It does occur.
Yeah, so a very common class of models are ones where you have leaks in every single compartment, yeah. And actually there's even very common structures of the graphs. There's, I can talk about it a bit more later after on, but yeah. So on that same thread, a very common assumption, in addition to the leak assumption, is having a strongly connected graph. So this is going to be my third assumption, that we're only going to be looking at models that have strongly connected graphs. So strongly connected meaning there exists a path from each vertex to every other vertex. And for the purposes of what I'm going to be doing today, I'm going to have an upper bound on the number of edges we're going to consider in our graphs. So we're only going to look at graphs that have at most 2n minus 2 edges, and the reason for this will come up a bit later on. Okay, so these are my assumptions. All right, so as we mentioned, we're looking at this class of linear models, input-output in the first compartment, leaks from every compartment, strongly connected graph. So the identifiability question is, which parameters of my model can be determined from input-output data? Well, in order for me to answer this question, I need to somehow relate my parameters to my input and output, because the way they're related right now is in this ODE system. But this ODE system is also in terms of unmeasured state variables. So what we'd like to do is eliminate out all the unmeasured state variables and get equations that are purely in terms of input, output, and parameters. So that's called finding the input-output equation. So I'm going to discuss that now. So I do want to mention that today we're just looking at linear models, and in order to do this trick of finding the input-output equation, we can actually just use a linear algebra trick. We can actually just use Cramer's rule to do this. But I want to mention in the general case for nonlinear models, you have to use differential algebra techniques, which I think Gleb will probably be talking about tomorrow. So there are some differential algebra techniques, some differential elimination techniques to do this in general. But for us right now, since our model is linear, we can avoid all that and just do a nice linear algebra trick. So the way this works is we're going to rewrite our system in this form. So we're going to factor it in this form, d times I minus a times x equals u, where here d is the differential operator d dt, I is the identity matrix. So now, using Cramer's rule, I get an expression for x1. In other words, in the denominator, I have the determinant of this matrix di minus a, and in the numerator, we replace the first column by u, but recall u is of the form u1 and then a bunch of zeros beneath it. So that means we can further simplify this as the determinant of this submatrix times u1, where I'm going to call this submatrix a1. So this is a matrix where I eliminate the first row and first column of a. Okay, so why does this help us? Well, y equals...
Can I ask this? So u doesn't commute with delta. Yes, because it's function.
Right. So yeah.
So you write it on the left. That is okay. Sorry. Yeah.
Yeah. So it's sort of just a little trick that we're doing, and so then we can then. So why does this help? So we can plug in y equals x1, and then cross multiplying, we get this form of this input-output equation. So notice that in this equation, this is we have our input variables, our output variables, and our parameters, which are the entries of a and a1. So you may notice that this equation has kind of a nice algebraic structure to it. On the left, we have the characteristic polynomial of a, and on the right, we have the characteristic polynomial of a1. So we can expand this out, apply the derivative, and we get an nth order linear equation where on the left we have these n coefficients of our characteristic polynomial of a, and on the right we have these n minus 1 coefficients, and those are the coefficients of the characteristic polynomial of a1. So in total we have these two n minus 1 coefficients, and they're just polynomial functions of my parameters. Okay. So in this so-called differential algebra approach to identifiability, we make the following assumption. We assume we have perfect data. So what does that mean? Well, we assume that we know y prime, y double prime, u prime, u double prime, etc. We're assuming we know these functions perfectly. So we're assuming we know them at many, many time instances, t1, t2, t3, etc. So what this means is that you could imagine taking your input-output equations and evaluating them at t1, t2, t3, etc. And what you would get is you get a linear system of equations and those coefficients, and we're assuming that you can uniquely recover values of these coefficients from our data. So that's our first assumption. We're assuming that we can recover values of these coefficients from our perfect data. So we're talking about perfect data here, yes?
And in actual modeling, what are the typical values of n?
The typical values of what?
N, the order.
Oh, I mean, so that's the number of state variables. So that.
What Can it be 2?
Sure. I mean, so yeah, so that's the number of compartments you could, I mean, it varies in the applications, but sometimes you have just models with just a few compartments, but typically I don't think they're more than 20, let's say. Like it's, yeah.
So between 2 and 20.
Sure, something like that. Yeah, you don't usually have too many compartments in these, for typical applications. All right.
Can I also ask,
yes.
Is it true that this is the smallest order input-output equation?
Yes. And so you end up getting that this is an order n, so it's the number of state variables, because this is algebraically observable, because it's strongly connected. So there are some results about when you get a differential order n, and it's n.
So it's minimal possible order because of this assumption of
strongly connected. Exactly.
Okay.
Yes.
Okay. Thank you.
All right. So so we get this input-output equation. We're assuming we can recover values of the coefficients. So then the identifiability question is it possible to recover the parameters from these coefficients? Okay, so why wouldn't we be able to do that? Well, what if, for example, two sets of parameter values yielded the same coefficient values? So what we're really asking is the coefficient map 1-to-1? So is the mapping from my parameters to these coefficients, is that a 1-to-1 map? Or more? Yes.
The previous slide.
Yes. Sorry.
So the reference that you gave, are these, so what is the purpose of the citations?
Oh, so in these citations?
Mm-hmm.
Oh, sorry. So so this idea of recovering the coefficients from the data. So I think Soderstrom and Stoica talked about this idea of persistence of excitation of inputs. And then Young and Glad were the first to bring up this notion of structural identifiability using this differential algebra approach. So that's why I cited them there. So they're
the input-output equation first appeared more or less in that paper.
Yes, I think so. Yeah.
Okay. Thank you.
Uh-huh. All right. So. Okay, so more generally or more formally, identifiability is a question of injectivity of this coefficient map, which in our case we're mapping from m plus n parameters, so that's the number of edges plus the number of vertices, to 2n minus 1 coefficients. That was the number of coefficients of the characteristic polynomials of a and a1. So then we say if our map is 1-to-1, we say our model is globally identifiable. If it's finite to 1, we say it's locally identifiable, and if it's infinite to 1, we say it's unidentifiable. And I should mention in this talk today, when I say identifiability, I really mean generic identifiability. So even though I don't always say it, I mean our identifiability holds everywhere except possibly on a set of measure 0. And specifically today, I'm going to be concerned with generic local identifiability. So today, I'm really just going to be concerned with this question: is our coefficient map generically finite to 1 or infinite to 1? So is our model locally identifiable or unidentifiable? That's the question I'm going to be asking. So if that's our concern, then if we want to check identifiability, all we have to do is just check the dimension of the image of our coefficient map and compare that to the number of parameters. So if that equals the number of parameters, we say our model is locally identifiable. But if it's strictly less than the number of parameters, then we say our model is unidentifiable. Okay, so how do we do this? Well, we can do the standard approach, which is to find the Jacobian of our coefficient map, evaluate it at some generic point, and then find the rank of that matrix. So that'll give us the dimension of the image of our coefficient map. So let's go ahead and try this out with our two-compartment model. So this is our model. Let's find the input-output equation. So notice on the left, we have these coefficients of the characteristic polynomial of A. So you may recognize the negative trace and the determinant there. And then on the right, it would just be for the 1-by-1 matrix A22. So we have these three coefficients.
Maybe I should have asked this earlier, but do we really, is it important that input is of this form? So they'll much change if I replace the vector u1, 0 with like u1, u2.
Oh, it does change. So then I have a sum of, then I'll have, so going back to our Kramer's rule, when I'm
so
evaluating, you would have sum of two of this. Take something with U1 and something with U2.
Different story.
Yes, exactly.
Okay.
Yeah. Yeah, so the whole reason part of the reason I'm making this assumption of single input and single output is because of this beautiful fact that we get just the coefficients of the characteristic polynomial for A and A1. If we had U2, then when you're working out the determinant, you don't actually, you're not going to get the coefficients of the characteristic polynomial, you're going to get something else. So that's what's nice about this assumption. So when the input and output are in the same compartment, you get this nice fact. So that's going to help us later on algebraically. Okay, so then...
But there are also real situations in which just one medication is given.
Right, exactly.
Yeah, but I mean, it will be the same if U1 will be at another position.
Yes, exactly, as long as they're in the same compartment. Is that what you're asking?
So no, if vector will be like 0 U1.
If it was 0 U1, then...
It will be different also.
It would be different, yeah.
Okay.
Right. Yeah, so you can still use that like Kramer's rule trick, I'm saying, but you just won't get the same fact about having all of your coefficients be coefficients of characteristic polynomials of some matrices. That's what I'm saying. But I can work it out with you. It's there's a little trick to find those as well. Okay, so you get these three coefficients. So what's our mapping then? So our mapping is from 4 parameters to 3 coefficients, and our question is this generically finite to 1? Of course, we immediately know the answer is no. We can find the Jacobian, evaluate it at some generic point. Here the rank is generically 3, not 4, so our model is unidentifiable. And of course that should really come as no surprise because we were mapping from 4 parameters to 3 coefficients. But what's interesting is with the current assumptions I'm making, which are single input-output in the same compartment, leaks from every compartment, and having a strongly connected graph, all of the models with these assumptions are going to be unidentifiable. And the simplest way to see that is with a strongly connected graph, at a very minimum, you have just a cycle. So at a very minimum, you have n edges. So at a very minimum, we're mapping from 2n parameters to 2n minus 1 coefficients. So every model with these assumptions is going to be unidentifiable. So then that leads us to this next question. Well, what do? We have an unidentifiable model. What's the goal now? What do we want to do? So we can't determine all of the parameters, but perhaps there's some combination of the parameters that we can determine. So perhaps we can determine the sum or the product of the parameters. So that leads to this notion of what we're going to call an identifiable function. So we say a function is identifiable if the field extension resulting from adjoining f to our field of rational functions and the coefficients, if that is an algebraic field extension. Or alternatively, we could say that our function is identifiable if it can be written as a function of my coefficients, because the intuition here is that if our coefficients can be determined from input-output data, then some function of those coefficients can also be determined. Thus, they are identifiable. Okay.
And so why not just relate so the coefficients of the input-output equation, why not just call it by the new parameters? So
the coefficients are identifiable. Yes. So the question is, can we find simpler functions? And I'll explain why. So why do we want to find simpler functions? Well, our goal is we want to try to reparametrize over those. And the problem is oftentimes those coefficients are very long, big polynomials, right? So we want to find the simplest possible polynomial functions that are identifiable. So I'll explain why. The goal is to reparametrize. Okay, so we have these 3 coefficients. So what are some nice simple functions that are identifiable? Well, it turns out these monomials, a11, a22, and a12 times a21, those are identifiable because those can be written as functions of my coefficients. So they're clearly algebraic over this field of functions in my coefficients.
And let's call one question. Sorry. But do you also set a goal that you can somehow rewrite the original system using what you're going to find?
Mm-hmm. Yes. Okay. Yeah, exactly. Right. So that brings exactly me to this question you're about to ask: is what do we do with these identifiable functions? And another interesting question biologically is: do they have any special meaning in the original model? Okay, so I'd actually like to answer that second question first. So to answer that question, let's go back to the graph interpretation of our model. So remember we said we're looking at models that correspond to strongly connected graphs. And in our case, our model just corresponds to this cycle between compartments 1 and 2. So notice that we can associate this cycle between vertices 1 and 2 with the monomial a12 times a21. And likewise, we can associate the monomials a11 and a22 with sort of self-cycles around 1 and around 2. So these three identifiable functions correspond to the cycles in the graph, which is actually kind of nice. And this is not just true for this model. This is actually true for all models with these assumptions I've made. So input, output in the first compartment, leaks from every compartment, strongly connected graph. So our coefficient map, actually, for all these types of models, can be written in terms of the cycles of the graph. In other words, it factors through the cycles. And the reason for this is due to this famous Leibniz formula for writing the determinant. In other words, we can write the determinant in terms of cycles. So why does this work out in our case? Well, remember, our coefficient map has the coefficients of the characteristic polynomials of A and A1. And the coefficients of the characteristic polynomial are just sums of determinants of various sizes. So thus, since we can write determinants in terms of cycles, then that's why our coefficient map can be written in terms of cycles. Yeah?
Why can we write determinant in terms of cycles?
So the determinant, I'm saying the determinant can be written in terms of these things I call the monomial cycles. So this is just this description of this Leibniz formula for a determinant.
Yeah, and so is it true that like this product in this sum, every product is a product of cycles of the graph?
Yes, exactly. So yeah, exactly. Products of cycles and for all your monomial terms.
Okay, I see. Mm-hmm.
Okay, so then this explains why, one of the reasons why we had this assumption about strongly connected, because in a strongly connected graph, you have the property that every edge is contained in a cycle. So the reason we want that to be the case is if there was some edge that wasn't contained in a cycle, then it wouldn't appear in my coefficient map, and then there'd be no chance of trying to find an identifiable reparametrization. So that's another reason why we assume strongly connected. Also, it's a well-known fact that for strongly connected graphs, you have exactly m minus n plus 1 independent cycles in the graph, where here m is the number of edges, n is the number of vertices. So we combine that with the fact that we have these n self-cycles corresponding to the diagonal elements, and we get a total of m plus 1 cycles. So that gives us an upper bound on the dimension of the image of our coefficient map. In other words, since the coefficient map factors through the cycles, this means we have at most m plus 1 as our upper bound for our dimension of our image of our coefficient map. Well, then this explains why in this two-compartment model our cycles were identifiable, because in that case the dimension was actually maximal. We had the full m plus 1, in this case 2 plus 1 was 3. So the way we can see this is that, let's say we call G our cycle map, and we can form this commutative diagram where we can write our cycles in terms of some function of our coefficient function. So thus our cycles are identifiable. Okay, well, going back to our model, we have this unidentifiable model. We've just found these three identifiable functions. The question is, what do we do now? Well, what we'd like to do is somehow reparametrize our model to go from 4 parameters to 3 parameters, where our 3 parameters are precisely these 3 identifiable functions. So that's our goal. All right, so let's go ahead and define what we mean by an identifiable reparametrization. So in our case, we're mapping from m plus n parameters to 2n minus 1 coefficients. So we say an identifiable reparametrization is a map Q such that C of Q has the same image as our original coefficient map C, and C of Q is finite to 1. So we have an identifiable reparametrization. So our goal is to find this map Q. Okay, well, when it comes to reparametrizations, we have a lot of possibilities here. So how do we choose a type of reparametrization? Well, a common thing to do is we don't want to sort of mess with the biology in the model. We want to sort of respect the original biological interpretation of the model. So a standard way to do this is to do a scaling. So we're just going to scale our state variables by some function in the parameters, and then we're going to rename that quantity capital Xi. And we'll see in just a few slides, this basically amounts to sort of like a non-dimensionalization. Okay, so a couple things to note. The first is that, recall y equals x1, so I don't want to mess with the first compartment. I don't want to scale x1, so we'll set f1 to be 1. Another thing to note is that because my model is linear, the effect of the scaling is actually quite nice. It just, what it does to my matrix is it changes the entries aij to be aij times fi divided by fj. So I have this nice simple formula. And finally, the effect of doing, the whole point of doing this scaling is to try to decrease the dimension of the parameter space over our new parameters. And the problem is it can only decrease it by so much. So that enforces an upper bound on the number of edges we can consider in our graphs. So this is why I made this assumption earlier. It turns out we can only look at graphs with at most 2n minus 2 edges in this case. Okay, so going back to our two-compartment model, I claim one scaling that works is to scale x2 by a12, and we'll leave x1 alone. So notice when we do that, in this new system here, it's purely in terms of our identifiable functions. So it's in terms of these identifiable cycles. So if we wanted to, we could just rename those as our new parameters. Let's just call them qij. So now our new coefficient map C of q has the same image as our old coefficient map C, but now this is a one-to-one map. So this is an identifiable reparametrization. Okay, so you may be a little bit skeptical. That's good. You may say, why is this useful, right? Because what we've done, after all, we've taken x2, which we don't know, and then we've scaled it by a12, which we don't know. So we've done the scaling. How the heck could this be useful, right? So that's a perfectly valid question. Essentially what we're doing is a sort of a non-dimensionalization in the sense that the coefficient of x2 now in this first equation is 1. So why is this useful though? Well, the idea is that even though we don't know x2 and we don't know a12, we still know the qualitative behavior of capital X1 and capital X2. So even though I don't know the actual value of x2, I do know the entries of this matrix. So that means I can determine the eigenvalues, and thus I can determine, are these functions increasing or are they decreasing? So I know the qualitative behavior, I know where they're increasing or decreasing, but I just don't know the units. I don't know the units because of this scaling by an unidentifiable parameter. So that's still useful information to know, qualitatively whether your functions are increasing or decreasing, but you just don't know the actual, absolute value. You don't know the units. So but that's sort of the best we can hope for when we do this type of reparametrization. Okay, so this worked out well for this two-compartment model, but of course the all-important question is, does this always work? And you may recall on the very first slide I said this doesn't always work. So in the first model I mentioned here, we had no identifiable scaling reparametrization, whereas the second model I mentioned does. So that leads us to this question, which models have an identifiable scaling reparametrization? So I'll go ahead and state our main result. We found that a model has an identifiable scaling reparametrization if and only if this scaling can be done by monomial functions of the parameters. This is true if and only if all the cycles in my graph are identifiable, and this is true if and only if the dimension of the image of my coefficient map is maximal. It's m plus 1. Okay, so let me go ahead and demonstrate this on our two examples. So for this first model...
And is it very fast to test it?
To test the dimension of the image? Yeah, sure. I mean, just find the Jacobian and evaluate it. Yeah, at a generic point. Yeah. So So for this model, we can find the coefficient map, find the Jacobian. It turns out the dimension of the image of the coefficient map is only 4, not 5, which is what was required. So this model has no identifiable scaling reparametrization. There still may be some other type of reparametrization, but no scaling reparametrization. So that's the key thing here. So who knows? There might be some other type, but there's not a scaling. On the other hand, the second model does have the correct dimension of the image of the coefficient map. So we can find. So this means that the 5 cycles, the 5 independent cycles in my graph are identifiable. So thus we can find a reparametrization. So I want to very, very briefly talk about our algorithm to find this reparametrization. What you do is you start by forming a spanning tree of our graph. And a spanning tree is a subgraph with n-1 edges that contains no cycles. We form the directed incidence matrix, and I'll demonstrate this on.
You don't care about direction of edges, so you take spanning tree.
Right. So I just can't. I don't want cycles. Yeah, but I select n-1 edges, but I don't want to pick cycles. So then I'm going to remove the first row, and then I'm going to find the inverse of that matrix, and the columns of that matrix are my exponent vectors of my scaling monomials. Let me go ahead and demonstrate this on our example. Okay, so for this model, we can pick a spanning tree. So for example, I pick these 2 edges here, the edges going to 1 from 2 and to 2 from 3. Then I can form the directed incidence matrix. So here, the first column corresponds to the edge going to 1 from 2, and the second column corresponds to the edge going to 2 from 3. So then I want to remove the first row, find the inverse of that matrix, and the columns of this matrix are the exponent vectors of my scaling monomials. So here, A12 corresponds to 1, 0. And then A12, A23 corresponds to 1, 1. So those are the exponent vectors of my monomials there. So once I have these scaling polynomials, to find my matrix, remember it's just Aij times Fi divided by Fj. So now I get this nice, simple, identifiable scaling reparametrization. And notice the entries in this matrix are purely in terms of the cycles. So I have an identifiable reparametrization. Okay. So this condition we just talked about.
Can you ask a question? Do you have an algorithm, and what will happen if you run this algorithm on the model that doesn't have reparametrization?
Oh, actually, I've never tried it.
Because
so you're saying on the case
it looks like it produced something in any case.
Well, yeah. So it'll produce, so in that case, the main issue is that your identifiable functions aren't necessarily just monomials. So you can get some type of scaling, but then that scaling won't correspond to a scaling over identifiable functions. It'll correspond to just some. Do you see what I'm saying? You'll be scaling your system, but the resulting matrix won't necessarily be in terms of identifiable functions, because your functions that are identifiable may be more complicated polynomials. And I'll show for the first model what you get for the identifiable functions.
So just in short, don't sense right that it will produce something, but this something doesn't make biological sense.
Yeah, well,
that doesn't make sense.
It's still going to be unidentifiable. That's the problem.
It makes sense, but it cannot be calculated.
Right, exactly. So it's still unidentifiable. You've probably decreased the number of parameters, but you haven't. It's not overall identifiable.
So I decrease the badness of the problem, but it's still bad.
Yes. Exactly.
So it's anyway good. I mean, it's in a bit
better.
Yeah,
sure, exactly.
Okay.
Right. Okay, so we've described this condition, and this condition was in terms of the dimension of the image of the coefficient map, which we said isn't too hard to calculate. But what would be really nice, it would be really nice if we could just look at a model and say, aha, this model has an identifiable scaling reparametrization or not. So we asked this question, which graphs have this property? And we have some partial results on this. We found that graphs that are inductively strongly connected have this property. So inductively strongly connected means there exists an ordering of the vertices starting at vertex 1, such that each induced subgraph is strongly connected. So here's an example of an inductively strongly connected graph. So here, the subgraph with 1, 2, that's strongly connected, with 1, 2, 3, that's strongly connected, and then the full graph is strongly connected.
May I ask a question? So you say you'd like to look at the system and decide, if it has but I thought you gave a.
So the condition was on the coefficient map, and I'm saying it'd be nice to just look from the graph itself.
And why?
Just
Curiosity.
for the biologist, it'd be nice for the biologist to know, looking at a model just looking at the graph itself. It'd be nice to know without having to do any calculations.
Okay, so if you use just a pen.
Exactly. Right. So we did find this result that inductively strongly connected graphs have this property. So here's an example of a graph that's not inductively strongly connected, and the corresponding model here does not have an identifiable scaling reparametrization.
But like if you take 4, 3,
it's starting at 1. It has to start at 1. Sorry.
Okay.
So 1 is the special compartment because that's the input-output
because
compartment.
there is one special.
So that's why we start at 1 because 1 is that special compartment. Yes. Good point. So unfortunately, though, this is just a sufficient condition, not a necessary condition, because here's an example of a graph that is not inductively strongly connected. However, the corresponding model with input-output at 1 and leaks from every compartment, that model has, and it unfortunately has a identifiable scaling reparametrization. So this is still an open question, this question of can we determine a complete characterization of this problem?
And what happens if we start with a bad model, the one that you erased, crossed, and so apply once and apply one more time. What happens the second time?
You mean try to...
No, but second time it will not be
so
after you run your algorithm once.
So you're saying if I scale the bad model and I do what Gleb was proposing, still scale it. Is that what you're saying?
So could you go back?
Yeah.
This was a good example.
This was a good example, yeah.
Do you have a bad example with?
So yes, I'm going to show. So the whole problem is that the identifiable functions in the bad case, I'll show them. They're polynomials. They're not monomials. So what's going to happen is, with this type of scaling, I'm not going to get These aren't the functions I'm going to get here aren't the parameters I'm going to get here aren't identifiable. That's the main issue. So the identifiable parameters are going to be some polynomial functions of those.
So. What if? But it's still possible to reparameterize the other one. In some way.
Well, but not necessarily, not via scaling. There may be some other type of reparameterization. Yes, it might be affine or something, but we don't know. I mean, there's not a clear algorithm for finding that reparameterization.
So that is not clear. But if we get such a form for that bad example.
Yeah.
What happens if we run it again? It won't make sense because it won't satisfy you.
Well, it still won't, exactly. It still won't, you're not going to get around that problem. You're still going to have your identifiable functions are going to be, polynomials. They're not going to be these monomials. So we're not going to be able to do this type of scaling. So, we won't get anywhere again. Yeah. So I don't think it'll help. Yeah. So now I want to step back a little bit. So in the remaining time I have, I just want to talk about this question of finding identifiable functions in general. Because, for example, what if we were looking at a different class of models? Maybe we're looking at linear models that have different input-output leak assumptions. Or maybe we're looking at the same class of models, but we want to look at this bad case where the dimension of the image of the coefficient map isn't maximal, right? The question is, how do we find the simplest identifiable functions? Well, let's try to pose this a bit more algebraically. So the way we can think about this is we have this field extension given by this field of rational functions and the coefficients, and I'm just going to label them C1 through Cm now because we're talking about the problem in general. The goal is to find a nice transcendence basis. So what do we mean by this? Well, let's say we have D algebraically independent coefficients, because they may not all be independent. So let's say D of them are independent. What we want to do is we want to find D algebraically independent functions that are algebraic over my field of rational functions and the coefficients. And we want these to be nice. We want them to be as simple as possible. So we want them to be low degree, few number of terms, maybe have some nice biological interpretation. But part of the problem here is that there's not a mathematically precise way of defining what we mean by simplest identifiable functions. So what I'm going to show you are some heuristic methods for finding these. So the first one involves Gröbner bases. So going back to our identifiability test, let's say we have our coefficient map and we want to determine if it's injective. We could do the standard test, which is say, okay, you have your coefficients C of P, set them equal to C of P star, where P star is some arbitrary point, and say, does P equal P star, right? So that's our standard injectivity test. So let's do that. So let's look at the ideal generated by C of P minus C of P star. So if we can find polynomials in this sort of separated, decoupled form, function in P minus function in P star, then these are identifiable. And how do we find these? Well, we can use Gröbner bases. So what we want to do is find sparse polynomials like this by using different elimination orderings with our Gröbner bases. Of course, the problem is here we don't know a priori what are good elimination orderings. So we may have to run this process for many different Gröbner bases. We may have to find Gröbner bases for many different elimination orderings. So that's part of the issue here. But let's go ahead and try this out. So with our two-compartment model, we can form the ideal generated by C of P minus C of P star. We can find a Gröbner basis. And notice in this case we luck out, because the three elements of our Gröbner basis have this nice separated, decoupled function in P minus function in P star, so thus these three functions are identifiable. But clearly here we lucked out, because there's no reason why a Gröbner basis would have this property, right? There's nothing in the definition of a Gröbner basis that says keep those separated. So for example, trying this on our model, which we called Model 2, this was the three-compartment model that did have identifiable cycles. We can find a Gröbner basis, and in this case, we're not quite so lucky. The first four terms, which I've highlighted in red, all of those you can sort of factor or separate out the function in P minus the function in P star. But these last two elements, we're not so lucky. They don't, the P and the P star are coupled, and we're not able to easily separate them. So for example, this last cycle here, this monomial term, in order to find that is identifiable, we would probably need to find a Gröbner basis where we eliminate those parameters last. Here we're eliminating those parameters first. We probably have to find one where we eliminate those last in hopes of trying to find those identifiable functions, but again, of course, we don't know a priori how many elimination orderings to check. So that's one of the main issues here. And of course, Gröbner bases can be very computationally expensive. So back to the drawing board. So then the question is, well, what else can we try? Well, going back to our test, we said we test for local identifiability using the Jacobian. And we said that we can tell if a model is locally identifiable or not by finding the rank of the Jacobian. Well, it turns out the Jacobian can be used not just to test whether or not a model is identifiable, it can be used to test whether or not a function is identifiable. So we have the following proposition. We say a function is identifiable if and only if its gradient is in the row span of my Jacobian. So let's try this out on our two-compartment model. We have our coefficient map. We can test this out on this monomial a12 times a21. So let's find its gradient. And clearly this row vector is in the row span of the Jacobian. It's not too hard to see. For example, multiply the first row by a22, add it to the second row, multiply this by a11 minus a22, add it to the second row and negate, and you get that vector. Okay, well that's great, but what this proposition tells us is if I have a function f, it tells me whether or not it's identifiable, but unfortunately it doesn't give me a way of constructing functions f such that their gradient is in the row span. So how do we do that? That's really the question. So how do I find functions f that have this property? This is where homogeneous polynomials come to the rescue. So you may have noticed on all those linear compartment models, the coefficient functions were always homogeneous polynomials. So I'm going to go ahead and state this proposition for homogeneous polynomials, and then I'll talk about later what to do if our functions are non-homogeneous. So what do we have? Let's say we take a vector in the row span of our Jacobian, but over this special field, this field of rational functions and my coefficients, then if I take that vector and dot it with my parameter vector, I'm gonna get an identifiable function. And the reason for this, it's just a simple consequence of Euler's homogeneous function theorem, which says that if you take a homogeneous polynomial, take its gradient, and dot it with its argument vector, you get the polynomial back, but scaled by its degree. So that's precisely what we're doing here. We're taking linear combinations of the gradients of our coefficient polynomials with weightings that are just functions in the coefficients. So when we take their dot product with the parameters, I'm going to get some function of my coefficients. So thus they're going to be identifiable. So let's check this out. We have our coefficient map. Let's find the Jacobian and let's apply Gaussian elimination over this field. Notice I get this nice simple triangular form here. And I can take these row vectors, dot them with my parameter vector, and I get these identifiable functions scaled by their degree, which of course I could then divide out, and we get the same identifiable functions from before.
Do you mean that the gradient of v dot p will be proportional to v?
So yeah, so V is something in the row. So V is of the form like F1 of C grad C1 plus F2 of C grad C2 plus da 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 da. And then I'm taking that linear combination of my gradients and then I'm dotting it with the parameter vector. So since each of the coefficients are homogeneous, when I take that dot product, I'm going to get a scaling of those original coefficient functions. So that way I'm going to get a sum function of coefficients. So I'm going to get an identifiable function.
I see. That's why, why you take this field. Not,
yes, exactly. That's why I take that field, yeah.
And is it true that any locally identifiable function can be generated by this procedure?
Oh, any
homogeneous?
I think so. So the main issue here, which I'm going to get to, is that you can always generate identifiable functions, but they may just not be simple. You may get really, obviously, super complicated identifiable functions. But yeah, so let me just finish up with the non-homogeneous point. If they're non-homogeneous, the idea is you can homogenize with respect to some variable, call it z, and then add z to your list of coefficients, apply the same process, and then set z to 1 in the end, and we get identifiable functions. So let me just, in the last few minutes I have, let me just demonstrate this out. So this was model 1. This is that model that was bad, that it didn't have identifiable cycles. So let's try this out. We can find our Jacobian with respect to some parameter ordering, which determines the ordering of my columns. I can apply this Gaussian elimination procedure, take my rows, dot them with my parameter vector, and notice my identifiable functions are the following. I get these two monomials, then I have this sum here and this difference here. So those are my sort of simplest identifiable functions using this approach. Of course, this depends on the ordering of my columns, because of course I could choose a different parameter ordering corresponding to a different column ordering. And then, for example, the result of my Gaussian elimination may give me, totally different identifiable functions. In this case, I get 3 of the same ones from before, but this fourth one is rather complicated. So the main issue with this method is that, we may, just like with the Gröbner basis method, where I don't know a priori which elimination orderings to choose, I don't know a priori what are the best parameter orderings to choose here. So I may have to apply this Gaussian elimination process to different column orderings. But the hope here is that, first of all, that the nice thing is that this method always finds identifiable functions, because at any point in my Gaussian elimination process, I can take a row vector, dot it with my parameter vector, and get an identifiable function. Versus with the Gröbner basis approach, I was specifically looking for elements that had this nice decoupled form, which I may not always have. So on the one hand, this is nice because this method always gives us identifiable functions. They just may not be very simple. So the idea is we still may have to apply this for many different column orderings to sort of generate a list of identifiable functions and find the simplest ones among those. And of course, the hope here is that since Gaussian elimination is a lot less computationally expensive than Gröbner bases, the hope is that this will work better for large models with lots of parameters. Okay, so I'll go ahead and end there. Thank you so much.
Thank you.
Do you have an algorithm?
Sorry?
Do you have an algorithm?
For this Gaussian elimination? Yeah, I do have one. Yeah, it's I have it written in Mathematica. I haven't published it or anything, but yeah. So it's yeah, I should do that soon.
And one more question. I think I missed the. You mentioned that the significance of the scaling reparametrization
Yes.
is to get some kind of qualitative.
Yeah. So the idea is that. Yeah. Let me go back to that slide. So the idea is that so the problem is that we don't know those functions, right? So we don't know x2 and we don't know. Let me put this back on here. So the issue is that we don't know x2. x2 is a unmeasured state variable, and I don't know a12. a12 is an unidentifiable parameter. So the point is that, you know, I don't know capital X2 then, but I know its qualitative behavior because of the fact, for example, that since this is a linear system here, I can determine the eigenvalues, so I can know, you know, if these functions are increasing or if they're decreasing. So I know qualitatively, I know, you know, if these functions are increasing or decreasing, but I know where they're increasing or decreasing, but I don't know the units because of this scaling by an unidentifiable parameter. So that's what I mean by we get the qualitative behavior of these functions, but we don't know the absolute values. We know the relative changes, but we don't know the absolute values. But that's sort of the best we can hope for. So in typical biological applications, you either do this, you either do a scaling, or if the experiment allows it, you would just take more measurements. So you could, for example, with this model, if I just also measure the second compartment, the organ compartment, then my model becomes identifiable. So if we have the luxury of changing our experiment and measuring something else, then that will help. But if we don't have that luxury, if I can't just, you know, maybe for some reason with the experiment, maybe I can't, like with our example, there's an organ, right, the heart, maybe I can't directly measure the heart or something. So if I can't directly do that, this is sort of the best I can hope for. So, you know, I find this, I end up getting the qualitative behavior of these solutions, but I don't know their exact values. So that's the best we can hope for.
And but you would know the signs, right?
Yes.
Of the unknown parameters.
Yes. Yeah.
Okay.
Is it that actually in this case we can find capital X2? Like it is known, we can compute it. Because like if you look at the first equation, then like capital X1 prime we know, A11 we know, U1 we know, so actually we know capital X2 also.
Oh, in this particular case, you're saying.
Yeah, but and actually like yeah.
But that's not always true. Yeah.
This is not always.
Yeah.
That was
yeah. Sorry. So this model was a little too simple.
So,
yeah.
Okay, but in general, it is not true that you can identify the initial values of these new rescaled things, or you can. Here you can.
The initial values, sorry, which of
capital X2, capital X3, and
oh, I'm assuming I don't know the initial conditions.
Yeah, but I mean, in this situation, you can find them, and is it true that maybe you can always find them?
Well, you know x1 of 0. Well, why do you know x2 of 0? Oh,
yeah,
for this particular case, but
yeah, but I mean, is it general situation or it's just lucky?
I think it's lucky. I don't think. Yeah, I don't think in general. Like if we just had a 3-compartment model, like let's go back to the 3-compartment. This one.
Yeah, you can still find X2.
So, yeah, but I.
And maybe if you take one derivative, maybe you can find X3 also. I mean, if you just differentiate the first equation.
You can find with X3 you can find from the second equation.
Yeah, the second. Yeah, I think.
It's no X2. Yes.
Yeah.
So maybe it's actually. I mean, maybe it's actually always happens.
I'm not sure. It's a good question. We might have just lucked out in these. I'm not sure, but yeah, you're right. I should think about that. That's a good question.
But not in the first one.
Right.
Yeah, but in the first
Yeah.
one you
You
didn't do
didn't have
scaling.
a, yeah. you
I mean,
didn't
this is
scale.
after scaling.
Yeah.
Ah, okay.
Because
Okay, this is
before you
after
don't know the
Before we
parameters.
don't know. Okay. And did you have a calculation what your algorithm would output in the for the first model?
No, so I didn't, so we found those identifiable functions, but I didn't even attempt a scaling. So I didn't even try to do a scaling. Yeah.
Is there any way to get access to your presentation, or it's?
Sorry?
It's being recorded.
Okay.
Oh yeah, it's being recorded, yeah.
I tried to go online, but it was trying some.
I can send you the slides as well, Alexi.